In this BME 271 lecture, we will give an introduction to and motivation for sensing position and displacement, and then we will start to talk about resistive displacement sensors. So we now turn our attention to sensing mechanical transduction. And specifically, we will discuss sensing two types of positions or displacements, which can be categorized as linear displacements or angular displacements or rotations. Our motivation for doing this is that it is often important to measure the size, shape, position of an object, movement of tissues, organs, instruments or controls. For example, in the OR kinds of engineering developments that Dr. Galloway is concerned with, he has to look at precisely determining the position of a given instrument that the surgeon is holding with respect to the tissue. And specifically, we will discuss sensors capable of relative measurements that are referenced to an immediately previous measurement. Right, so you don't necessarily know the absolute position or angle of something, but you know how far it's gone since we started measuring it. And we'll also look at methods for doing absolute measurements that'll be referenced to some fixed 0 point in a coordinate system. Like if we define some given rotation to be 0 degrees, we will look at ways to measure an absolute rotation from that point. So some considerations that we have to think about when we're designing or choosing a device here. We have to think about whether what we need are relative or absolute measurements. We have to ask ourselves whether we want linear or rotary displacement, want to measure linear or rotary displacement, or angular displacement. Are we going to expect small or large displacements? What is the resolution that we need? What will be the rate of our movement? The expected rate of movement? Or velocity, or angular or linear velocity? Can the transducer keep up with that rate of movement? What will be the cost? Of course, that's always a consideration, regardless of what we're measuring. And is there any? Will it make contact with a tissue? Is it non-contact? If it does make contact, will there be some required starting force to start making any measurement? And will that required starting force impede the very motion that we are trying to measure? We're going to look at a number of different transducer types. We'll first start out by today talking about resistive transducer types. So these will be linear transducers, rotary transducers. These are essentially different types of potentiometers, different configurations of potentiometers. And then we'll also talk about strain gauges. We'll talk about encoders, incremental encoders that rely on a rolling ball or wheel. And we essentially have to sense what angle do they tick through. And then we'll also look at absolute angular encoders. and those will be optical, based on optics. We'll talk about capacitive displacement sensors, inductive displacement sensors, such as the LVDT displacement sensor that we talked about when we were talking about inductance to voltage conversion, the linear variable differential transformer. And we'll talk about rotary, essentially a rotary version of the same concept. This is called a synchro resolver. Or an RVDT. And then later we'll also talk about triangulation and time of flight. So we will start by talking about resistive position sensors. Now recall the resistance equation, which we've seen in a few different contexts now, that resistance in ohms is given by the resistivity of a given material that the resistor is made out of times the length of the material that you have divided by the cross-sectional area of the material. And so here we're going to look at two types of sensors whose resistance varies through different influences on L, the length, and A, the area. And the two types we'll be looking at will be potentiometers and strain gauges. We'll start with potentiometers, which are the most common. So potentiometers are the most common type of resistive position sensor, and they use mechanical sweepers or wipers, also called wipers, to vary the length of two resistors, the relative length of two resistors. So here are two common potentiometer types. There are three common potentiometer types. This is the one we're probably used to from lab. So this is able to give us a measurement of linear translation, right? So it's got 3 ports, one here, and one here. And we measure the output voltage across it. That depends on the position of the, it's a voltage divider, and it depends on the position of the wiper along this resistance. So we can measure any given displacement within this range. We also have a single turn rotary or angular potentiometer. So here we tap out the resistance right here with this wiper, and that's connected to some center point, which then conducts over to the output terminal of the device. But it's again just a voltage divider where you have one leg here, one resistor here, and one resistor there, and the relative length changes. The third type is also a rotary or angular encoder, but can go through multiple turns. So now you have a wiper that goes through a corkscrew, that can go through a corkscrew kind of pattern, or maybe the resistors themselves go through a corkscrew kind of pattern, and so you can imagine then that you can go through multiple angular turns and resolve larger than 360-degree rotations. And again, to emphasize, these all work as voltage dividers. They all work the same way as voltage dividers in a circuit. So let's look a little bit more closely at translational potentiometers. So let's draw one here. So there's the full resistor, and then we tap it out somewhere along its length. And so this is plus and minus of V out. The distance, let's reference the distance of the wiper from the bottom. We'll call that x, the displacement, and we'll call the total length of it L. So then we can write, if we have a V in here, let's say that this is ground, and this is V in, then we can write the V out has to be equal to V in times the fractional, times the relative resistance of the bottom leg, as we typically have for a voltage divider. So that will be rho times x over A, while the total resistance of the device is going to be rho times L over A. Of course, the rhos and the A's cancel out, and we are left with a very simple expression that V in, or that V out is equal to V in times x over L. So then immediately you can appreciate that V out is going to be linearly proportional to displacement. Now let's also look at a rotational potentiometer. Let's say that we have this device. It's a circle of resistance. And let's say that we have a wiper sitting here, sampling our output voltage. And here's the negative voltage and positive voltage of Vin. And we'll say that Vout shares the same negative terminal as Vin, as per usual. So the wiper is at some position theta. Of course, the potentiometer can't close all the way perfectly to 2 pi, can't go perfectly all the way to 2 pi around, since you have to have some gap between the terminals so they don't touch each other. So in this, the wiper will be at some given position theta, some given angular position theta, while the maximum possible rotation will be some other angle theta max, which will be slightly less than pi. So we have to think about now the circumference if we're trying to calculate the total resistance. And what we get when we consider the circumference of it is that we have Vout is proportional to Vin, again, times rho over A times 2 pi, we've got to get the circumference of the guy, times R, times the fraction of the circumference that the wiper has swept through. Okay, so that would be theta over 2 pi. Of course, the 2 pi's then cancel. Divided by rho over A, which again then cancels just with the top, times 2 times pi times R times theta max over 2 pi. And again, the 2 pi's cancel here too. The R's also cancel. And so what we get is this drastically reduced equation that Vout is equal to Vin times theta, the angle that the wiper has gone through, divided by theta max, the maximum possible angle for it to go through. And we then get that Vout is linearly proportional to angular position. So to conclude, some of the advantages of potentiometers are that they are very simple, they are very cheap, costing mere cents on the dollar, they enable a measurement over a pretty wide displacement range, which you can obviously mechanically amplify in various ways. They are easily built into circuits just because they're so simple. Sorry about that. They allow you to make continuous measurements, meaning that you can measure Vout once and then measure it again and continuously. So long as Vin is on all the time, you can measure Vout at any point in time and determine the displacement. Some of the disadvantages include the fact that the mechanical impedance of them, input impedance, can be relatively high, meaning that it can take a fair amount of force to get them to move, a relatively high amount of force to get them to move, which then can end up impeding the very motion you're trying to measure. When they get worn out, they get a little bit noisy. Sorry, that's supposed to be an arrow here. So you need to clean them from time to time because they're a mechanical part and they can get dust inside there and such. I recently, for example, had to clean out the potentiometers on my guitar. Since where you have the knobs, those are potentiometers as well, right? Rotational potentiometers. And sometimes after a while they start to get a bunch of gunk in there, and you got to spray them out and to wipe off to clean off the conductors inside. They can be nonlinear when they are loaded with subsequent circuitry. That is, when Vout is attached to something with sub-infinite input impedance. So when it's attached to a circuit with a low Zn. And finally, if you have wrapped wire, as many of them are made out of, is this very high gauge, or so very thin, wrapped wire, then you are effectively sliding the wiper along different points along this wire, and so different turns, and so each turn gives you a different V out, but that it's going to jump in discrete amounts, which then can limit your resolution. So the idea is that you form the potentiometer from this wrapped wire that looks like that, and as you move the slider from one turn of the wire to the next, that's how you get your change in resistance, and that can then, because you have to make these discrete jumps in the turns, you get a certain limit in your resolution. Okay, so now let's do a practice problem with potentiometers. Let's think about the circuit below here. This is going to be a translational potentiometer, and let's say it has a total resistance of R and a total length of 1 centimeter. Okay, and then we have the wiper, which at any given point in time will be at some point along this curve, and it's referenced there, and Vn positive is up top and V out is here. Okay, and then the displacement at any given point in time is this x variable here. Okay, so here Vn will be equal to 1 volt and R will be equal to 5 kiloohms. So the first thing to do that I'd like you to do is plot V out as a function of x. So V out should be on the y-axis and x should be on the x-axis for L equals 1 centimeter, as I have drawn here, and x between 0 and 1 centimeter, so the full span, right? So x equals 0 is this point and x equals 1 is that point. So I'll give you guys a few seconds here to do that. So here's the solution. We have V out here on the y-axis, x is on the x-axis, and it's just going to be a straight line, right? It's going to go from 0 to 1 in x and 0 to 1 in V out, using the previous potentiometer equation translational potentiometer equation that we showed on a few slides ago. So now let's consider a problem where we have the potentiometer connected to some output circuit with finite input impedance. So now we've got the potentiometer here again, and it's got the same Vn, same length and everything. It'll be L equals 1 centimeter and R equals 5 kiloohms. And we're going to have it now attached to, we're going to be measuring V out across the input impedance of some amplifier or filter or whatever circuit, and then it's going to be grounded. Sorry, and this is going to be another resistance, R sub L, the load resistance or the input impedance of the subsequent circuitry. Okay, so now the question I'd like to posit is, when x is 0.5 centimeters, meaning right in the middle here, right here's x. Again, it's referenced the same way as on the previous page. So there's x, and if it's right in the middle of the potentiometer at 0.5 centimeters, what is the position error if the load is 5 kiloohms or if the load is 50 kiloohms. So I'll give you some time to work on that too. Okay, here's my solution. So in this case, we can write down the voltage divider equation here, and what we have in this configuration is that Vout is equal to the input voltage times this voltage divider equation here, right? So we have the load impedance, the 5 kiloohms load impedance, in parallel with half of the potentiometer impedance if X is 0.5 centimeters. So that's the 2.5 kiloohms here. So it's 5 parallel 2.5. And then that is forming a voltage divider with the upper half of the potentiometer, which is another 2.5 K. Okay, so if we calculate all this out, all the algebra out here, we get 0.4 volts for Vout. Whereas if we had no loading on it, if we had an infinite RL, what we would get is 0.5 volts. And we saw from the previous part A of this problem that X equals Vout. Right? We have a linear relationship with a slope of 1 between X and Vout. So X equals Vout. So this is an error of 0.1 centimeters. Right? It would be 0.5 minus 0.4 gives 0.1 centimeters. Okay, so now I'll give you a few minutes to look at the 50 kiloohm case. So what we do is we follow the same procedure here, but just replace the 5 kiloohms with the 50 kiloohms, and this is what we get, is at 0.49 volts. So now you can see that the error is actually going to be 0.5 minus 0.49, which is 0.01 centimeters error, which is 1/10 of the error here. Right here we again said it was 0.1 centimeters error. So clearly, as we increase the loading impedance of the output circuit, as we increase the input impedance of the output circuit that we connect Vout to, we are going to get more accurate measurements. So this is something you have to keep in mind, though, when you're connecting up potentiometers to subsequent circuitry. Okay, let's move on to strain gauges. So strain gauges are devices that essentially comprise a set of wires that get stretched somehow, and they exploit changes in the wire's conductivity, rho, their length, and their area that occur when the wire is stretched within its elastic limit. And they are usually used to measure the force creating the stretch by mounting the wires to some cantilever or diaphragm. Sorry, that should be an or. And all three parameters, rho, L, and A, will change as the wire stretches. So there are two general types here. We have the bonded strain gauge, where the wires are actually glued or somehow attached to some backing material, and they get stretched not a heck of a lot, actually. So this is good for measuring, for more sensitive measurements, where both the wire and the backing is stretched a little bit. So usually you have to improve sensitivity, you have multiple lengths of the wire, right? It will be folded back on itself multiple times on the substrate to which it is attached. And here's an example of an unbonded strain gauge where we've actually set it up to measure the fluid pressure, like blood pressure, for example. So what we have here is that blood or whatever fluid will come in here, and then it will push against this piston, and then it will exit here. And this piston will move back and forth along this direction, and the piston will be attached to this large armature. So it's like a block, essentially, that it's attached to, and so the block also is moving back and forth with the piston's motion. And what we do is we attach these 4 wires to it, for example. So you have this wire A here that is attached to the armature, and then some point on this side of the armature. Then B is attached to the opposite point, opposite end of the substrate from the armature, and to this point on the armature. And then C also has the same orientation as B, and then D has the same orientation as A. So what you can see what happened here is that if you push the piston this way, then you're going to get the wires B and C are stretching, while if the piston is relaxed, meaning there's less blood pushing into it, then the whole armature is going to move that way, and you're going to have A and D will be more stretched than B and C. So you're going to get opposite changes in the wire's resistance. So B, C, and A, D are going to have opposite changes in their resistance depending on the push on the diaphragm. And so what you do is you orient them. You put them into a Wheatstone bridge. You have to put basically put, for example, you'd put B and C perhaps along in R2 and R4. This explains it more. But what you need to do is have opposite changes on each leg. So you'd have, for example, wire B attached here, wire C attached here, wire A attached there, and wire D attached here. And then you get opposite changes on the top and bottom for the two sides. And you can measure it with a Wheatstone bridge then. Okay, there's a third type of strain gauge which is called an elastic strain gauge, which is good for measuring much larger displacements. So elastic strain gauges are devices that can measure large displacements, like up to 50% of their relaxed length. And so for these strain gauges, really only L and A change, not the conductivity itself. And of course, actually with the bonded and unbonded, it's also primarily L and A that change, though rho also changes a little bit. Here's an example of a commercial elastic strain gauge. It's hard to find a decent picture here, but essentially what it is it's just two electrodes connected to a plastic tube that's filled with, or this flexible tube that's filled with an electrolyte paste. And so it's just essentially one long wire that can change length by quite a large range in response to respiration, in response to stretching due to respiration. So you put this belt around a subject's chest, and then as they breathe, the belt is going to stretch or contract. So now let's look at some theory of strain gauges. So neglecting the change in conductivity that we would get with stretching, because as I said, it plays a relatively minor role. When a fine wire will be stretched, of course, by conservation of mass, its area is going to decrease. Its cross-sectional area will decrease, but its length will increase. And as a consequence, its resistance will increase. And it turns out that it varies linearly with strain. Now, expressing R, the total resistance of the wire, as some base relaxed resistance plus the change in resistance due to the stretching, we get that delta R is equal to the base relaxed resistance divided by the base relaxed length times this factor G that I'll define next times the change in length. So the change in resistance is approximately proportional to the change in length. So G here is what's called the gauge factor. It's also called the strain sensitivity. And G is a material-dependent property that can be defined mathematically as the ratio of the change in resistance to the change in length for a given conductor. Okay? And so it's called you can restate this as being the fractional change in resistance divided by unit strain. So some typical values for the gauge factor. Note that gauge in English, in British English, is G-A-G-E, and in American English is G-A-U-G-E. So you'll see these both appearing in the literature, and I certainly didn't know that until I started teaching this material. So some typical G values are about 2 for most metals, but for semiconductors you can get strain factors of about gauge sensitivities of about 100. But semiconductors are less linear and are more sensitive to changes in temperature. So they can be a lot more sensitive, but you have to control for these other factors such as nonlinearity and temperature sensitivity. Now, since the change in resistance is usually going to be quite small relative to the relaxed resistance, strain gauges are usually used in bridge circuits. And if they're semiconductors, then we'll use at least 2 in a circuit, in a bridge circuit, to reduce errors due to the change in temperature. So they should be going opposite directions so the temperature change subtracts off. Okay, so some advantages to strain gauges include the fact that we can measure very small displacements. In fact, it is possible to measure nanometer level displacements. You can also get a continuous measurement, just as with the potentiometers. There will be later on some position sensors that we'll talk about that you cannot make continuous measurements with. That's why we make the distinction here. Their disadvantages include the fact that they have a temperature sensitivity, because again the conductivity can be temperature sensitive, or as I said, the semiconductor strain gauges are sensitive to temperature. So you got to ask yourself then, is this change in resistance that we're seeing due to a change in temperature or a true change in length? And with most of them, you can only measure small deflections. I actually had a really hard time even finding examples of the elastic strain gauges. Okay, so that concludes this lecture.